This video is introducing the reaction system of oxidation reduction for organic compounds. This is a pretty significant reaction type for our course, so we're spending a fair amount of time on it in the remainder of the course. I'd like to introduce it for us by beginning with this overview of the different categories of organic compounds. Often these are called functional groups. And I've listed all of them here, alkanes all the way over to amines. I'd like to categorize these a little bit more though, these different functional groups. Specifically, I'd like to categorize them by looking at how many bonds to oxygen is being made by carbon in that compound. As we'll see in just a moment, that's a key part of understanding the oxidation of these compounds. On the far left, you notice the hydrocarbons, alkanes and alkenes. Those have only carbon and hydrogens, and so of course there are 0 bonds to oxygen. In the middle of your screen, you see a whole bunch of different functional groups, all of which have carbon, hydrogen, and oxygen. Alcohols, ethers, aldehydes, ketones, carboxylic acids, and carboxylic esters, often just called esters, those all have carbon, hydrogen, and oxygen. But you'll notice I've separated those even a little bit more into 3 categories. Alcohols and ethers have just 1 bond to oxygen on the carbon. Aldehydes and ketones, you'll notice carbon is making 2 bonds to oxygen. And then on carboxylic acids and esters, carbon is making 3 bonds to oxygen. That again will be the foundation for us making sense of organic redox. On the far right, the amines, I didn't make any comment on that because there is no oxygen. So let's take a look. The oxidation, the reactions that we'll be looking at are for the functional groups that I've circled here. We are not talking about ethers really at all in this course, so I've crossed those out. Alcohol, aldehydes, ketones, and carboxylic acids. That's what we'll see in this video, is what happens when those undergo or try to participate in an oxidation reaction. The way that I will introduce this whole topic of organic redox is with this second handout that you see on the screen in front of you. It's a fairly busy handout, I recognize that, so I'd like to break it down for you just a little bit. We'll start with what's on the bottom right there. I've called out that writing on the bottom right of your slide, which is the definition of oxidation and reduction. We have talked a little bit before about redox reactions. We talked about them in the context of inorganic redox. And in that context, we learned that oxidation means losing electrons and reduction means gaining electrons. That is still true. In fact, that is the universal definition of oxidation and reduction. So that is true. But in addition to that, we are planning to think about oxidation in a new way, a way that'll make a little bit more sense for organic compounds, be a little bit easier for organic compounds, apply to organic compounds. It's still true that oxidation is losing electrons, and it's still true that reduction is gaining electrons. But now that we are not dealing with compounds where we see cations and anions, this second way of thinking of oxidation and reduction will be more helpful to us. Specifically, we're looking at whether the carbon in that compound is gaining bonds to oxygen or whether it is losing bonds to oxygen. I'd like to highlight the gaining bonds to oxygen because that's mostly what our focus will be. That's actually where that word oxidation comes from. Oxygen, gaining bonds to oxygen. Carbon, of course, always has to have 4 bonds. It cannot have 5 or 3. So if it gains 1 or more bonds to oxygen, then it has to lose 1 or more bonds. When carbon loses bonds in an oxidation reaction, those bonds will be to hydrogen. So if carbon gains 1 bond to oxygen, it will lose 1 bond to hydrogen. If it gains 2 bonds to oxygen, it will lose 2 bonds to hydrogen. Reduction is the opposite. It continues to be the opposite of oxidation. So if oxidation is gaining bonds to oxygen, then reduction is losing bonds to oxygen. If oxidation is losing hydrogen, then reduction is gaining hydrogen. And hopefully this makes sense to you. Carbon needs 4 bonds. So in reduction, if carbon loses bonds to oxygen, then it needs to gain bonds to something and that something is H. So that's our introductory overview of how do we think about oxidation and reduction, not in terms of electrons, but in terms of oxygen. Now let's keep going with how would we make this happen if we're working with these reactions in the lab. So I'll call it another part of this slide, the bottom left of this slide. The bottom left of the slide is talking about oxidizing agents. And I wrote here, I said, if you want to oxidize something, anything, you'll need to mix that something with an oxidizing agent. The oxidizing agent is the thing that makes oxidation happen. The oxidizing agent itself, it would get reduced. Its partner would get oxidized, it would get reduced. So the oxidizing agent will make oxidation happen. Common oxidizing agents in the lab are the three that I've listed on the slide for you. I've written them in the color that they actually exist. The sodium dichromate solution is a bright orange. It's actually the dichromate ion, the dichromate anion that's doing the oxidizing. Sodium is just a spectator ion. In other words, potassium dichromate would also work, but we most commonly work with sodium dichromate, which is bright orange. It's an oxidizing agent. The second common oxidizing agent we work with is Benedict's. Sometimes it's called Benedict's solution, sometimes it's called Benedict's reagent. Those are the same things. Benedict's is a bright blue, and I've indicated it here as blue. The third kind of common oxidizing agent that we might work with is called Tollens reagent. The Tollens test is sometimes called the silver mirror test. One of the product when a reaction happens with Tollens is silver, and it looks like silver. It's bright and shiny. And if it's coating the inside of a test tube, then it looks like a mirror. So Tollens solution, Tollens reagent, that's an oxidizing agent. You'll notice that I've separated those into two categories, strong and weak. I'm going to hold off on discussing that until we get a little further into this video, so I will come back to this, but sodium dichromate is classified as a strong oxidizing agent. Benedict's and Tollens are classified as weak oxidizing agents. And I will point out right now, though, strong and weak in this context is not talking about strong and weak oxidizing or strong and weak acid and base, for example. When we talk about strong acids and strong bases, that's something very different. So I will give an example a little while later in this video what we mean by strong and weak. Now we can take a look at the last part of this slide, which is the top. The top of this slide is a summary of all of the redox reactions that involve those functional groups I highlighted at the beginning of this video. So we will spend the rest of this video looking at the top of this slide. And to make it a little bit easier to do so, I'm going to have us focus just on that. So this is the top of that previous slide, kind of zoomed in. You'll notice on the far left of this slide, I have alcohol on the far left, and then in the middle row I have alcohol on the far left, and in the bottom row I have alcohol on the far left. I will start us out by helping you notice what's the difference between those three alcohols that I have listed. We'll start up at the top. I've listed that as a primary alcohol. The number 1 with the little degree sign next to it, you would pronounce that primary. What does this mean? If you take a look at the alcohol functional group itself, which is OH on a carbon, so I've circled that in red. The OH itself is not the alcohol. Alcohol is OH on a carbon. So there it is, I've circled that in red. To classify the alcohol as primary or secondary or tertiary, to classify it, you identify the alcohol functional group as I've done, I've circled it in red, and then look to see how many bonds to carbon are attached to that functional group. I'm trying to be very clear. I'm not going to have you count how many carbons are attached. Instead, you're saying how many bonds to carbon are sticking off that alcohol group. And I can see in that top alcohol, it's just one. There's only one bond to carbon sticking off. And since it's one, that top alcohol is classified as a primary alcohol. The one below it, I've circled again circled the alcohol functional group, and I notice that in this case there are 2 bonds to carbon attached to that alcohol functional group. There's one bond attached pointing to the left, and there's a second bond pointing to the right. Again, I'm not counting carbons, I'm counting bonds. Since there are 2 bonds to carbon attached to the alcohol, that that alcohol is classified as a secondary alcohol. And the way that you would write that is a 2 with a little degree sign. Finally, the bottom alcohol, again, I've circled the alcohol functional group, and then what we will do is count how many bonds to carbon are attached. We're not counting carbon atoms, we're counting bonds to carbon, and I see that there are 3. One pointing to the left, one pointing to the right, and one pointing down. So this one is classified as a tertiary alcohol. 3 with a little degree sign is tertiary. The reason I'm listing these differently or showing each of them on this slide is it turns out that their reactivity is different. What primary alcohols do with their oxidizing agent is different than what a secondary alcohol does with an oxidizing agent, and that's different from what a tertiary alcohol does. So we will look at each of those 3 right now. Going back to the top, we'll start with primary alcohol. Our question will be, what happens if we mix this primary alcohol with an oxidizing agent? Now you'll notice something here. You'll notice I haven't listed what is the oxidizing agent. In fact, all that I've done is I've written the letters OX above the arrow. That OX above the arrow indicates that we're trying to oxidize that reactant. We're trying to oxidize the primary alcohol. We don't even indicate what is the oxidizing agent because that's not our focus of what's happening. We actually don't really care what happens to that oxidizing agent. We know it will get reduced, but we won't even discuss what does it turn into. Our focus is entirely on what happens to this alcohol. So the OX is a way to indicate what is the reaction type. It's oxidation. We know there's an oxidizing agent, but we're not even identifying what it is. So how do you know what to do? How do you know how to complete this reaction? This is what I will do for each of these examples and any further examples that we do. You focus on the carbon that has O attached to it. And notice I still have this circled in red. The carbon that's not inside that red circle, nothing will happen to it. It will still be there. We won't erase it or get rid of it, but it will not change. It'll stay just as it is. The carbon that does have an oxygen bonded to it, which is the one inside the red circle, that's the one that will change. And remember how we started this video. We said oxidation is gaining bonds to O. So sure enough, the carbon that I've circled, we will try to see if it can gain bonds to O, because that's what oxidation is. You might also recall that oxidation involves losing H. We will not try to keep track of where the H is going or where does the H come from when it gets lost. We're not going to keep track of H's. We're strictly focusing on oxygen. That will be the most straightforward way to always figure out what the product will be. So when I look at this primary alcohol, what I will do, what I will have you do is, if you are doing this on a piece of paper, you would erase that H, or you would redraw that alcohol with the H not showing. Or if you're on your computer right now, take your thumb and cover up that H. The H needs to get invisible so we can focus just on carbon and oxygen. When we do that, I would have you ask this question: is there room on that carbon, the carbon that has the O on it, is there room on that carbon for any more bonds to oxygen? And there are. Right now, there are only 2 bonds showing. We know that there's more to hydrogen, but we're focusing on the bonds that are showing. Carbon is making 1 bond to the other carbon and 1 bond up to the oxygen. So we do have space for another. And when I allow 1 more bond to O, that's what I've circled it over in the middle. I allow there to be another bond to oxygen. Notice, of course, oxygen cannot have 3 bonds. So notice that hydrogen that used to be up on that top oxygen has to go away. Hydrogen will just go away as needed to make space for more bonds to oxygen. Now, of course, it can't just disappear and be gone. Where did that hydrogen go? It becomes part of the other product. The other product, the one that we are not identifying or worrying about, that's where it goes. So we won't be keeping track of it, but that's where it goes. Then we say, hey, that aldehyde is still, or that compound, that product is still in the test tube or still in the beaker with that same oxidizing agent. Could it keep reacting? Our way to find out is we say, I don't know, let's find out. And recall, the way that we'll find out is saying, look at the carbon that has bonds to oxygen already. and I've circled that there in the middle. Does that same carbon have room for any more bonds to O? Right now, the carbon inside that red circle in the middle is using up 2 of its bonds to an oxygen, a 3rd bond to the carbon. The 4th bond, though, remember, we've erased the hydrogen, or we've ignored it, or we've covered it up with our thumb so that it doesn't confuse us. And so that would help me see, yes, I do have room for more bonds to O. 2 bonds go to O, the 3rd is to carbon, but that means a 4th bond can go to oxygen. And that's what I'm showing in that 3rd red circle. I'd like you to notice that it's not possible to have a triple bond between carbon and oxygen. Carbon can do triple bonds, but oxygen cannot. Oxygen can only make 2 bonds. So if we want carbon to have 3 bonds to O, then it will look like I've shown in that 3rd red circle. So if we double check, the carbon inside that red circle it does not have 5 bonds or 3, it is showing 4 bonds. We'll ask ourselves, could that compound keep going? Could that get oxidized? That answer is no. The carbon inside the red circle is using up all 4 of its bonds to oxygen or carbon. There are no bonds to hydrogen we could kick off. I do need to draw in a hydrogen on that other oxygen. Oxygen does need to have 2 bonds. So the top oxygen is using both of its bonds to carbon. The oxygen off to the right is using 1 bond to carbon, so the other would be to an H. When I wrote NR off on the far right, that's an abbreviation, kind of unofficially, for no reaction. There would be no reaction with that final compound because there's no room on that carbon for more bonds to O. What I've done in yellow, highlighted in yellow underneath each of those 3 compounds, is identify the functional group. On the far left, when we started, we had a primary alcohol. When the primary alcohol gets oxidized, it's no longer a primary alcohol, it makes an aldehyde. The middle compound is classified as an aldehyde. We said the aldehyde, if it's sitting in a test tube or beaker with that oxidizing agent, it will get oxidized also. And when an aldehyde gets oxidized, the classification of that product is carboxylic acid. Carboxylic acids cannot get oxidized, no reaction, because the carbon is full, has no more bonds. If I were to do this in the lab, if I were to pour a primary alcohol into a test tube and add some sodium dichromate or add Benedict's, my final product would be the carboxylic acid. That would be the answer. I showed you the aldehyde in the middle to help you step by step understand how the process happens, but it doesn't stop at the aldehyde. In fact, it's very difficult to get it to stop at the aldehyde. So if I were to ask you what happens when you oxidize a primary alcohol, the answer is the product is a carboxylic acid. If I try to oxidize an aldehyde, the product is also a carboxylic acid. What about secondary alcohols? What do you suppose is going to happen with a secondary alcohol? Let's take a look. Here's our secondary alcohol. And again, with your thumb, cover up the H or redraw that compound with no H showing or erase the H, because our focus will be, is there room on that carbon for any more bonds to O? And when I try to see if there is, I get that compound where carbon is making 2 bonds to O. There is room for 1 more bond to O. The way that happens is the H goes away. Notice that top oxygen with the double bond cannot have a hydrogen. Oxygen can only have 2 bonds. It cannot have 3. The H does not disappear. It becomes part of the other product. That product we just made is called a ketone. It's classified as a ketone. Can a ketone get oxidized? I don't know. Let's find out. We ask ourselves, that carbon that does have oxygen attached or bonded to it, is there room for any more bonds to oxygen? And the answer is no. Carbon is using up 2 of its bonds to oxygen and the other 2 to carbon in a ketone. So it doesn't have space for any more bonds to O, which is why I wrote NR. You cannot oxidize a ketone. Similarly, the very bottom one, tertiary alcohol, I've circled the alcohol functional group to help us identify the carbon that is involved. Is there space on that carbon for any more bonds to O? It's already using up 1 of its bonds for oxygen and the other 3 for carbon, so there is no space for any more bonds to O. This tells us that a tertiary alcohol does not get oxidized. If I try to summarize this, I have done that on this slide, helping you identify what actually of these functional groups can get oxidized. Primary alcohol can, aldehyde can, or secondary alcohol can. Those can get oxidized. The others cannot. Carboxylic acid we saw is NR, no reaction. Same with ketone, same with tertiary alcohols. The ones I've crossed out in red cannot get oxidized. I'm pointing this out because our final piece in this video is to try to make sense of the strong and weak oxidizing agents that I mentioned at the beginning. Focusing on the functional groups that can get oxidized, primary alcohol, secondary alcohol, and aldehyde. What's happening with strong versus weak? And I have listed those. You'll notice I have them written in orange and blue. Sodium dichromate in orange and then Benedix in blue. Benedix is a weak oxidizing agent. Sodium dichromate is strong. Here's the difference. A strong oxidizing agent, such as the orange sodium dichromate, will oxidize anything that can get oxidized. So primary alcohol, secondary alcohol, aldehyde, those can get oxidized, which means the strong oxidizing agent can do it. Sure enough, you'll notice right below those 3 green circles that I've written a plus sign next to sodium dichromate for all 3 of them. That means that those 3 functional groups would each give a positive dichromate test because they can get oxidized by the strong oxidizing agent. Weak oxidizing agent is as it sounds. It's just not that good of an oxidizing agent. It can only oxidize something that's pretty easy to get oxidized. That would be aldehyde. I like to think of it this way. Look visually at the screen in front of you. Aldehyde is kind of halfway done. The far left of the screen you could think of as the starting line, and the finish line is off to the right. The aldehyde is half done. It already has 2 of its bonds going to oxygen. The 2 alcohols only have 1 bond going to oxygen, so there's more work to be done. The weak oxidizing agent cannot oxidize those alcohols because there's too much work to do, and it's a weak oxidizing agent. So if you look at the blue letters, you'll see that there's a plus sign next to Benedix for aldehyde. That tells you that aldehyde will give a positive Benedix test. Another way of saying that is Benedix will react with an aldehyde. Aldehyde can get oxidized by Benedix. But if you look at the primary and secondary alcohols, you'll notice they have a negative sign next to the word Benedix. That tells you that those 2 types of alcohols will not react with Benedix. They do not get oxidized by Benedix. The 3 that are not in green circles, which are carboxylic acid, ketone, and tertiary alcohol, those do not get oxidized by any of the oxidizing agents because they don't get oxidized. This requires some practice. I will be providing practice, and I will be encouraging you to practice so that you can understand how these reactions work and you can predict products for a variety of compounds. But we'll always do it in the way that we just showed in this video. That's the end of this video. Thank you for listening.